see, start recording. Okay, let's get started. We are happy to have Yiwen Pan, who is going to tell us about the Schur correlation function and deformation quantization. Please. And if you have a question, just turn on the voice or raise your hand. I will try to find you. Yeah.
Okay, thank you. Let me first thank Satoshi to invite me and also for organizing this series of seminars. So today I would like to talk to you about this Schur correlation functions and deformation quantization. It's based on work with Wolfgang Pilas in Oxford. So let me begin with some introduction of the background material on this associate VOA and associate topological algebra or deformation quantization. So let us start with a four-dimensional n equals 2 super conformal field theory T on R4. Then in this paper by Bim, Lamos, Leandro, Pilas, and Rastelli, they study a class of special operators called Schur operators, O, which are put on a special complex plane inside this R4. And these special operators arise as cohomological classes of certain nilpotent supercharges. And at the origin, one can look at the harmonic representatives, and one can show that their charges satisfy these algebraic equations. But we want the operator to be defined on the whole complex plane. So they perform a so-called twisted translation onto the whole complex plane. So when you move the operator, you should also mix the SU2 components in the representation. And as a result, the twisted translated operator defined on the complex plane as a cohomological class is independent of the Z-bar, so it's holomorphic. And secondly, their OPE between them are also holomorphic. And that leads them to define a associated vertex operator algebra, which we will for now denote as this bolded V associated to this four-dimensional SCFT T. And this vertex operator algebra contains certain notable elements. For instance, if one starts with a four-dimensional SU2R current, and one of the components would descend to a element T, which is simply the stress tensor in the vertex operator algebra. And the two-dimensional algebra has central charge determined by the four-dimensional central charge C4D times this negative number minus 12. So therefore, this chiral algebra in two dimension is necessarily non-unitary if you start with a unitary theory in four dimension. And if you start with a flavor, the four-dimensional theory contains flavor symmetry, then the associated moment map operator will descend to Effen-Moody generators, current generators in the vertex operator algebra. And the corresponding level will be given by this formula. And this vertex operator algebra has the notion of conformal weight as usual, and is defined as E minus R, where R is the SU.
Sorry.
Yes.
Flavor symmetry means global gauge symmetry?
Yeah, global gauge symmetry.
Global, global symmetry?
So, just flavor symmetry, excluding the
flavor means not gauge symmetry.
Flavor means symmetry that commutes with supercharge the entire super algebra. So global symmetry.
Is it global symmetry?
Yes, it is. Yes, sorry.
Global, I see.
Yes, it is.
I see. And normally central charge is positive, right?
The C4D is usually positive.
But in your slide, it's given as negative.
Yes, so if you start with a unitary theory which has a positive C4D, you will get a negative C2D in two dimension in this chiral algebra.
Okay.
So you will get a non-unitary theory there.
I see. Non-unitary, I see.
Right. Good. So these Schur operators are counted by this Schur index, and it's defined as a super trace over all the operators in the SCFT in 4 dimension. And using the dictionary they discover, it can be rewritten as another super trace in the language of the vertex operator algebra. And it's clearly equal to so the Schur index on the left, a 4-dimensional observable, can be identified with the vacuum character of the associated vertex operator algebra. And as usual, by the radial quantization, the Schur index can be identified as an S3 times S1 partition function. On the right as well, we have this vacuum character can be identified as the torus partition function of the associated VOA. And among all the Schur operators, there are a special class of members, which are the the Higgs branch chiral operators. Their charges satisfy these relations, and the VEF parameterize the holomorphic function of the Higgs branch vacua, MH. And this MH is in fact encoded as in this following formula discovered by Beam and Rastali. So it's the space of holomorphic, the ring of holomorphic function of the Higgs branch vacua can be identified with the reduced C2 algebra of the VOA, sorry. And conversely, starting from this Higgs branch vacua, one can use a free field mechanism to recover the vertex operator itself. And this is discovered and discussed in Beam, Manajavali, and Rastali. So there are many, this is an active field, and there are many people working on this field, including some of in the audiences. So many theory has already has the non-associated VOA. For instance, the Lagrangian theory, the associated VOA can be built out of busy beta gamma system plus certain BRST procedure. And for class S theory and say for some TN theory, the generators are proposed in these papers. And for other theories like DC series and Julius-Douglas theories, their VOA are also studied extensively. And the simplest cases, they give Virasoro algebra or affine Kac-Moody algebra and so on. And they're studied by many people, Cordova, Shao, and Song Xiedan, and Wenbing Yan, and many others. And also, this story of VOA can be enriched by including surface defects or line defects in 4 dimension, and they are usually related to modules of the VOA. And they're studied by Cordova and Gaito and Shao, and Beam Rastali, and also Leshi Naka, Sasha, and Zhu.
Yiwen, what does DC stand for?
Oh, DC. DC is a series of complex Lie algebra, and okay. They are associated to a certain 40 SCFTs. Okay. Some F theory, a D4 band proving some singularity.
Oh, okay.
D3 band, sorry.
Okay,
yes.
Thanks.
Okay, this is the story of VOA, and then another story about topological algebras. So one can start with a 3D n equals 4 SCFT on R3, and the asymmetry would be of this form. So we have a part that acts on the Higgs branch and a part acting on the Coulomb branch. And in this paper by Beam, Pilas, and Rastelli, they discovered that there is a special subset of operators, which they would call a twisted translated Higgs branch operators, and also a counterpart in the Coulomb branch as well. But here I will focus on the Higgs branch version. So these operators arise again as cohomological classes of certain nucleon supercharges, and they are in one-to-one correspondence to Higgs branch chiral operators, whose charges satisfy this equation. And again, similar to the story before, their OPE along R is topological. So therefore, they use this set of operators to define an algebra, associated algebra DQ of T. So the product of these operators inside this algebra will be denoted by a star. And this star is associative. And moreover, the product is C star equivariant. And that means you take two operators that are associated to a particular SU2H charge, then the product will be a finite sum of operators with lower or equal SU2R charges. So explicitly, the SU2 is broken, but the associated filtration is preserved. And the star product of these operators have certain notable leading terms. For instance, the first term is simple.
Sorry. SU2 Higgs branch, when SU2 Higgs branch is broken, some Nambu-Goldstone boson appears?
Maybe not in this way. It's not really this, not some spontaneous symmetry breaking pattern. It's just this operator O itself is a mixture of different components of different in the SU2H representation. So the definition of the operator itself breaks the SU2H. It's not that the theory is spontaneously broken.
Oh, really? I see. Is it broken at the quantum level? Namely, is it something of anomaly?
I'm sorry, is it?
Breaking of SU2H is quantum anomaly?
No, it's just this operator algebra is defined in a way that it does not respect the SU2R charge.
I see.
So it's just you take two operator and you, the O itself does not have a well-defined notion of SU2R charge because it's a mixture of different R charges.
Okay.
So if you take two, since these operators are associated to Higgs branch chiral ring, so we can take F and G to be the homomorphic function of the Higgs branch vacua. And these two functions will be associated to two different Higgs branch operator. One can compute the star product, and the result will contain the first term. The leading term is the operator associated to the product of the F and G. That's the first simple term. And the next simple term is a term proportional to the operator associated to the Poisson bracket of these two functions on this function space. And of course, there are more terms behind. But the C star equivariance ensures that there's a finite number of terms. And it sometimes truncates more earlier than expected because of the SU2 selection rule. And therefore, this topological algebra, DQT, is a C star equivariant and associative deformation quantization of the Poisson algebra CMH. And of course, this MH itself is a hyperkähler cone. So that's one of the conclusions in that paper. And another important conclusion is that these deformation quantization of this hyperkähler cone are classified by this particular cohomology space. So an element inside this space are called Fi, associated to, in physics, Fi parameters. The Fi parameters are not turned on per se, but these are the potential Fi you can turn on to resolve the singular cone to a smooth manifold. And usually these these elements are called periods. And these are discussed in this paper.
What does M hat here?
Hat is called a symplectic resolution of this cone.
Oh, I see. How about WC?
No, it's not very important in the following discussion. It's just a notation.
Okay.
It's a symplectic resolution of this singular manifold. And one can compute the H2 and then models by some finite group.
Okay. And
yes.
you mentioned
they are, yes.
You mentioned that the Z graded. So where does this Z gradient come from?
It's actually come from the SU2R charge. So
Okay.
although this OI itself is so doesn't respect the SU2 symmetry, but the Higgs branch color ring itself does have a notion of SU2R charge.
Okay, thanks.
And the OI breaks this SU2R charge in a controlled way. So you can still recover some Z grading here.
Okay.
And this topological algebra can be computed concretely. So I can start from a SCFT, which flow from a, sorry, it should be 3D n equals 4 gauge theory. And this algebra can be computed by twisted Higgs branch correlation function defined on S1 inside an S3. This is computed by Tadashenko, Bufu, and Jacobi. And the computation is a localization computation with respect to a particular supercharge inside a super algebra, inside the superconformal algebra or in three-dimensional n equals 4 theory. And the result of localization is a Gaussian theory on S1 in this S1. And the very useful product of this computation is some integral formula for the Higgs branch operator correlation function. So one can concretely do the computation to recover this abstract algebra using these gentlemen's mechanism. So that leads us to the following question. First of all, we can observe that one can insert into the supertrace that defines the Schur index some Schur operators. And our question would be, can we produce a localization formula for these torus correlation function? And the second question is, can we extract the deformation quantization of the dimensional reduced SCFT from the vertex operator algebra associated to the four-dimensional SCFT? So this is a picture that connects various things, and our question is associated to this question mark here. And that is basically asking what is the dimensional reduction of the vertex operator algebra. And hopefully that will land us on to directly a deformation quantization of the 3D theory.
Sorry. How do you perform dimensional reduction?
So that would be so in here, computation is very simple. Just take a special limit of the correlation function, for instance. That shrinks the radius of the S1.
I see.
So remember, the Schur index can be defined as a S3 times S1 partition function, for instance. One can try to shrink the radius of this S1, and somehow that will land us on a three-dimensional world. And we would try to do it.
Does it has some relation with finite temperature? No.
High temperature, actually.
Okay. Then dimensional reduction means high temperature limit, right?
Exactly. Yes. So it's very clear.
Then in that case, contribution of fermion is dropped, right? Become ignorable, right?
Sorry, what?
In the high temperature limit, normally fermion becomes ignorable. Am I right?
Right, that would be one of our results. Maybe that's related to your comment. You see that the fermionic operator will decouple.
I see.
And I have one question. Can you go back one slide?
Yes.
You mentioned this theory from 40 n equal to 4.
It should be 3D.
What does it mean?
Huh?
It's a 3D. Oh, okay. I see.
Sorry.
Okay.
Okay, so let me start with the first part, the Schur correlation function. So as I mentioned before, the Schur index can be regarded as an S3 times S1 partition function. So that's why now we are looking at S3 times S1 as our localization manifold. So the S3 is parameterized by 3 coordinates, phi, chi, and theta. In particular, the M, the four-dimensional manifold, can be quotient out by this U1 chi, because the phi and chi's are periodic coordinates going from 0 to 2 pi. So we can perform a U1 motion, and that will land us onto a disk times S1. And it has a boundary, which I will call as a T2, theta equals 0. I will call it as a boundary torus. And this torus coincides with the locus of theta equals 0 inside M. So it's a special torus. And let me give it a coordinate Z. So to perform localization, we should first put a n equals 2 theory on this S3 times S1. And to do that, we apply this rigid limit of supergravity developed by Closet, Dimitriescu, Pastusia, Komaskowski, and Seiberg, and also in the context of localization by Peston, Hamohazomichi, and many others. And for us, the background we found depends on parameter tau, which essentially parameterizes length or the radius of the S1, the temporal S1, and also two other numbers of parameters, beta 1 and 2. And on this background, we found 4 Killing spinor solutions, and they span this particular superalgebra. And among these 4 supercharges, we choose one. And this one squares to some bosonic operators. And among them is a Killing vector that have this torus as fixed point. So we will expect the localization to localize onto something on this torus. And finally, another ingredient is that this beta 1 and beta 2 as parameter of the background has a special limit where this torus originally doesn't necessarily have the complex structure given by tau. But now in this special limit, which I call Kähler limit, this torus will have a complex structure given by tau. So these are basic ingredients of our localization. And there are some observations which are important for localization. First of all, the Yang-Mills action is exact with respect to all 4 supercharges that are supported by our background. So I would write as Yang-Mills equals delta of Cassi. And this Cassi depends on the Killing spinor that you choose, but in the end, I would ignore it in the notation. And some remarks follows. First of all, the Yang-Mills Lagrangian is a top component of a n equals 2 chiral multiplet, whose bottom component has a U1 charge 2. And this is discussed in Gomez and Istich. And this exactness tells us that whatever we compute by localization will be independent of the Yang-Mills coupling. And finally, this Yang-Mills action is a very good localizing action, a localizing term, because it has positive bosonic part. And secondly, using our background, we can look for some Q-closed operators. And indeed, we found some Q-closed operators QA, which are just combination of the hypermonoplex scalars, and some other almost BPS or almost Q-closed fields, combination lambda Z and lambda theta Z. And they are a combination of the gauginos in the vector multiplet. And they're almost BPS because their supersymmetry variation is proportional to the auxiliary field inside the vector multiplet. And of course, they are BPS and almost BPS only when they're inserted on the boundary torus. So next we can try to localize the Schur index. And the computation is very similar to what's done in the Lyshenko, Puffer, and Jacobi. So we write down the action to localize. We have the we have the hypermonoplet action, the Yang-Mills action with a coefficient S, frac S, and the standard localizing action for the hypermultiplet. And this action has a feature, very important feature, that is quadratic in the auxiliary field D. And we can crank up the localization machine. And we found for the vector multiplet, the BPS locus is parameterized by flat connections, and the rest are 0. While for the hypermultiplet localizing, the BPS locus is as follows. The hypermultiplet scalar are chi invariant, and they're controlled by some elliptic PDE defined on this three-dimensional manifold, the disk times S1. And therefore, the solution are determined by the boundary value QA on the boundary torus. So good. We can start to gather all the ingredients in the partition function. We have the classical contribution. We have this Yang-Mills action on the BPS and hyper on the BPS. The Yang-Mills gives 0 and the hyper gives something non-trivial. It's a beta-gamma system living on the boundary torus. The vector multiple one loop is simple because we know that from literature, and those results can be obtained by doing localization with respect to a supercharge inside one of the SU1/1. Our supercharge sits inside both SU1/1. So we can take their results and show that they can be rewritten as some T2 partition function of small BC ghost system. So these are very simple. And finally, the hypermultiplet one loop are conjectured to be 1. And this is checked in some examples. Now, all the ingredients we discover are independent of beta 1 and 2. The two parameters that parameterize the supersymmetric background. Since they are independent, so they're useless, we take the Taylor limit. The boundary torus will have tau as its complex moduli. So now we can rewrite the Schur index. The Schur index now takes the form of an integration over BPS locus, A, the flat connection, and Q, the boundary value of the hypermultiplet scalar, and also the BC ghost part. In total, the index is written as a path integral inside and a contour integral outside. Where inside we have BC gamma system, a BC beta gamma system. And of course, we can rewrite this thing into a very familiar form. We have this contour integral of Schur index with vector and hyper contribution. Those are just simple theta functions.
I have a question. What does small mean? Small BC ghost?
So small BC ghost means one should remove the 0 mode in C. Just you remove the 0 mode. And that's discovered in the original paper by Beam, Lemos, and friends.
Okay, thanks.
And the Gaugino lambda and lambda tilde would be identified with B and derivative on C. So therefore the 0 mode of C doesn't matter. Doesn't enter in the theory.
Okay,
removed.
Thanks.
So good, we have the Schur index under control. What about Schur operators? So as a start, we would guess what the Schur operators are for localization. And they're apparently gauge invariant words or operators composed of the letters in this line. We have the QA, we just defined before, and the Gauginos, and covariant derivative. And of course, we will want to insert them onto the boundary torus. But there's a problem. In general, these operators, O, composed of these things, are non-BPS, and in general, fermionic. But usually, in the usual localization argument, we want delta closed operators, namely BPS operators. And usually, we want bosonic insertion, because usually, if you want to insert fermionic operators, you better have some 0 mode in your Lagrangian of the fermionic Lagrangian. But in this case, on S3 times S1, the Dirac action doesn't have 0 mode. So there seems to be some trouble. So that leads us to a generalization of the usual localization argument. So in here, we will let the operator O inserted to depend on the S in front of the localization term, the Yang-Mills action. So we let the operator O to depend on S, and then we want to compute this entire path integral. Of course, when S equals to 1, we will go back to the original problem. And when S is equals to plus infinity, we hoped to have some localization, and we want these two limits to be equal. And therefore, we will impose the S independence of the entire correlation function. So take the derivative, we get two terms, and we want them to be 0. So that's we give it a simple name, localizability. It's for legally equating S goes to 1 limit and S equals to infinity limit. So we want to solve. We need to solve this path integral equation first before doing localization. So we look for localizable operators, and we found some. And these operators can be defined using these letters, which is basically the same as before, except that the gauge node contains a factor of square root of S. So we use them to form gauge invariant operators and put it on the S2. And moreover, we require them to satisfy an algebraic equation, delta OS on O should be 0. This delta OS is just the supersymmetry variation, but all the auxiliary field should be replaced by its on-shell value. So, and it's true for, and this equation is true for all Schur operators. And it's studied in this original paper. So essentially, we have turned this path integral problem into an algebraic problem. And the sketch of proof is as follows. The target is to show that these operators satisfy this equation. And the observation is that this C, which enters into the Yang-Mills action, it is at most linear in D with coefficients which looks like lambda Z and lambda tilde Z. And the second term, we can do a little, we can move the delta to act on the OS. And then since the delta OS contains D and the C contains D as well, so this expression contains 1 point and 2 point functions of the auxiliary field D. Now we can treat them separately. The 1 point function can be computed, and that spits out the on-shell supersymmetry variation. Well, the 2 point functions part of this expression will produce a term that completely cancels the first term here. And therefore, the original problem of the invariance of the VEF now turns into an algebraic equation. So all you need is this thing is 0. And they are satisfied by all Schur operators. And therefore, we can localize all Schur operators. And they contains fermionic and bosonic Schur operators. And the rest is basically autopilot. You put them into localization machine. And in the end, we will get that the Schur operator VEF, or correlation function, is computed by this integral, very simple contour integral. We have the usual one loop for the vector multiplet and hypermultiplet, and times some very simple free correlation function of the Gaussian theory, beta gamma BC system. And these can be computed via Wick contraction. So until now, we are able to compute the correlation function using localization. That would lead us to a second question, how to relate to the problem of deformation quantization. So here we ask the question, suppose we start with a 4-dimensional SCFT, and we know its VOA, and therefore we know, at least for Lagrangian theory, we know the correlation function. So we know the many things. And can we extract from this VOA the deformation quantization of the theory obtained as dimensional reduction of the 4D theory? This question, right off the bat, we know some partial answer and hint. For instance, the Higgs branch vacua is invariant under dimensional reduction. It is commonly believed to be true. And there's some more discussion in the recent paper by Teleshenko on the same question, to address the same question. And the second clue is that an observation that the Higgs branch Schur correlation function that we can compute by localization reduced to the topological correlation function studied in Teleshenko, Puffer, and Jacobi. Therefore, at least part of the question is correct, is known, that there are some p's of the VOA can be reduced to the deformation quantization of the dimensional reduced theory in 3 dimensions. However, there are some troubles. Our method before only applied, the localization computation only applies to Lagrangian theory, but we want to extend it to non-Lagrangian theory. And second, the vertex operator algebra associated to the SCFT contains too many operators. Most of them are spinful, so they contain spin and they're fermionic. And most of them are non-Higgs branch operators, but we only want Higgs branch operators in the 3 dimension. So we have to find a way to kick out all these excessive Schur operators. That leads us to the following proposal. Again, we start with the S3 times S1. And as before, we want to perform a dimensional reduction that instructs us to take the high temperature limit. We can identify tau, the complex structure, to I beta and set beta to +0. And then we can start doing the following thing. We will try to rescale every Schur operator O by a number beta to the h, where h is the conformal weight of the operator given by E minus R. And then we can compute the 1-point, 2-point, and 3-point functions of these operators, rescaled operators, and then take the beta goes to 0 limit. And that would give us some numbers, AUIs, and some 2-point functions, and some 3-point functions. And finally, given that there is some 1-point function here, we would like to perform a Gram-Schmidt procedure. First of all, we want to remove the 1-point function, and also we want to diagonalize the 2-point functions. And after this procedure, we claim that the result, all the correlation function, will be independent of the position except for the ordering. So it depends on the ordering only along the phi. So phi is one of the circles inside the S3. And second, we claim that the 3-point function that we get would be mostly 0 if any of the operator participating is a non-Higgs branch operator. Or in other words, if they have spin in 4 dimensions. And thirdly, if we take this 3-point coupling and then take the inverse matrix of B and then define this C, that would help us define a star product between these operators. And the final claim is that this star product defines a C star equivariant deformation of the 3-dimensional Higgs branch, and with a potential different period from the SCFT value, or the one that is predicted by the Bim-Vilas-Rastali paper. So there are some remarks about the procedure that we propose. First of all, the scaling factor can be motivated by the high temperature behavior of the correlation function, and which follows from the modular property. So they goes like beta to the minus conformal weights. So the scaling factor basically kills all these singularities. And they're topological using Joule's recursion. For instance, the 2-point function in the vertex operator algebra, the torus 2-point function, can be written as the first term involving the 0 mode of the operators, OO and OO prime, plus some more functions, complicated elliptic functions. But this elliptic function will vanish in the high temperature limit after rescaled by this beta h plus h prime. So that's where the topological or the dependence solely on the ordering comes from. And also we have the R filtration, basically because the original operator breaks the SU2R symmetry, but it preserves the SU2R filtration. And that leads us to the C star equivariance. And finally, we can look at this 0 mode part, and we can perform the commutator, and the leading term will indeed be a Poisson bracket of these 2 operators. And of course, there are some lower terms. And so from these evidence, we can claim that the star product that we define gives a C star equivariant deformation quantization of the Haber-Kähler cone, namely the X branch vacua. But there are other design properties that are less obvious in here. Those will be left for future study. So this proposal, we can give a Lagrangian proof for Lagrangian theory as follows. So first of all, we can make a very simple observation. If you start from the Schur index in 4 dimensions, you perform this high temperature limit, you will land on the 3-dimensional partition function of the, which is a Lagrangian theory, of course, with a Cardi behavior in front, which will be canceled in in computing correlation function because it's divided. This is the first hint. And the second, we can analyze all the Green's function in 4-dimensional computation on the, or the vertex Green's function on the torus. We study the high temperature limit. For instance, we can look at the Higgs branch 2-point function, namely the 2-point of Qs. And also we can look at the non-Higgs branch correlation function, namely those with Q but with some derivative, or those with the gaugiano with or without derivative. And they're inserted at different points. And third, we can look at these objects inserted at the same point, so Z1 equals Z2. And we can start all of these and study the high temperature limit of all of these objects. The result is that the first line and the last line survive the limit. And in particular, the C, the last line, these things captures the coupling between the Higgs branch and the non-Higgs branch operators. And we want to get rid of these non-Higgs branch operators. And that instructs us to do a Gram-Schmidt procedure to decouple all the non-Higgs branch operators. And of course, the remaining Higgs branch operators also need further diagonalization performed in Dedeschenko, Puffer, and Jacobi. And this is the this particular O hat is a new basis where the non-Higgs branch operators are decoupled from all the Higgs branch operators. So it's a partial diagonalization. So that's and of course, since now the problem separates into 2 parts. The first, one part is the Higgs branch operators, which we know that for Lagrangian theory will land us onto the computation of Dedeschenko, Puffer, and Jacobi. And their computation will lead to the deformation quantization of the SCFT. So this gives a Lagrangian proof of our proposal. But for non-Lagrangian theories, we will try some tests, simple tests. So we look at some very simple non-Lagrangian theory. For instance, we can look at the Aristocles theory, A1, A even, whose vertex operator algebra are known to be these Virasoro minimal models. And they have these theories have trivial Higgs branch, and therefore we expect a trivial deformation quantization as the outcome. So the Virasoro algebra contains only one generator, the stress tensor. So we only need to look at the correlation function of stress tensor. We can look at the Ward identities for stress tensor in this form. So on the right is some very simple objects plus some elliptic function, wire stress P function and zeta function and so on, and lower order coordinate function of stress tensor. Using these Ward identities or other recursion relations, we can define the new basis of stress tensor, just remove the 1-point function and show that after rescaling, the correlation function of T trivialized, and therefore we would get the trivial deformation quantization from this procedure as expected. And of course, we can generalize this argument to all theories, and therefore showing that the T hat, and namely the stress tensor with the 1-point function removed, indeed decouples from all correlation function in this procedure. So at least among all the Schur operators, the T is not in the game. It's ruled out. And this type of algebra-Stokes theory are related to the A1D odd series by Higgsing. And this theory contains a collection of Coulomb branch operators. And in the recent paper by Tedeshenko and Wang, they also discussed the reduction of the operator content as well. The next example we will look at is another simple theory, A1D4. And the VOA is easy, just affine Casimir algebra of SU3 of a certain level. And we want to compute the high temperature limit, so we look at the torus correlation function. And from our proposal, we can compute the star product again. And the result will match with the three favored SQED in 3 dimensions. And this dimensional reduction and the 3D mirror were studied in Schur, Beam, Rastey, and Tedeshenko, Puffer, and Jacobi as well. So again, we start from our 4D theory, perform the high temperature limit. We land directly on the deformation quantization of the dimensional reduction of the 4D theory. So that's good. And finally, final example is A1D odd series. Again, the VOA is very simple, just affine Casimir algebra of SU2. And there are a collection of Coulomb branch operators with non-half integer U1R charge or dimension. But after dimensional reduction, these R charges are supposed to be somehow related to the SU2C katan. But given that the RC in 3D is the katan of SU2, so it must take half integer value, and therefore there's some mismatch. And the rescue comes from the flavor symmetry in rotating the Coulomb branch Higgs vacua. Coulomb branch vacua. And these are the global symmetries of the 3-dimensional theory. And the S3 potential function would depend on this number C in front of this generator of the Coulomb branch global symmetry. They appear in the potential function as some imaginary Fi parameters studied in Buchan and Nishinaka. And studying the reduction of the Schur index to the 3-sphere potential function will give us some hint of what this number C is. And the result in our procedure gives us the following thing. First of all, there seems to be some free theory as the reduction as a result of taking high temperature limit plus a TSU2 theory. And the C, the coefficient responsible for the mixing between the global symmetry, the flavor symmetry, and the SU2C symmetry, is given by 1/2n + 1. And therefore, the reduction or the proposal that we have lands us on a deformation quantization, but it's not the same as the one associated to the SCFT as the dimensional reduction of the 4D theory. We land on a different value. And this happens when there's symmetry mixing between the R symmetry and the Coulomb branch or Higgs branch, the Coulomb branch flavor symmetry. So let's do a quick summary. And first of all, in this talk, we study this localization of Schur correlation function. And we need a slight generalization of the non-localization argument. And also we perform a dimensional reduction study of this Schur correlation function. And we get a topological correlation function as the outcome. And somehow it match in some cases with the deformation quantization of the 3D SCFT. And in some cases where there's symmetry mixing, the period will be moved away from the FCFT value. There are some interesting problems to explore in the future. For instance, the computation can be maybe carried out on S4. There has been a similar localization computation for potential function on S4, but it would be interesting to look at if one can compute Schur operators correlation function on S4. And of course, we can also address this computation with Schur surface defects, which is correspond to V modules. And would be interesting to study the reduction or the relation to deformation quantization associated to 3D SCFTs. And the V module associated to the SCFT in 4 dimension, there are some of them are very special. They appear in the S transformation of the Schur index, and they should be interpreted as certain special surface defects in the 4-dimensional SCFT. And also one can ask the question whether one can compute the Schur correlation function from the QR mu side, since we know that the Schur index can compute it using QR mus in 2 dimension. And of course, it would be interesting to study a further connection with deformation quantization from QR mu side. That would be the end of my talk. Thank you. Any questions?
Thank you very much. Any questions? If you have a question, please turn on the voice and then go ahead.
Can I ask a question?
Yes, please.
So in your dimensional reduction procedure, so in the case of 4D side, the Schur operator correlation function doesn't really depend on the ordering, but in the 3D case, in the topological quantum mechanics, it should crucially depend on the ordering of the operators. So exactly Indeed. Where you get that ordering?
Let me see. So computationally, we can see that depending on this, so doing this high temperature limit, for instance, for the very simple Green's function, it depends on the sign of Z1 minus Z2 in the limit. So it's invisible in 2 dimensions since you can move around.
Right.
But when you do the reduction, the 2 points are essentially geometrically, you can see that it sort of pull to the single line. And in the computationally, the reduction will look different if you have a Z1 minus, the real part of Z1 minus Z2 to be positive or negative. So you can see that directly in the computation. It rises naturally in the limit. Or you can feel that this, for instance, in here, it will contains 2 terms. One is responsible for stuff with Z1 minus Z2 having a positive real part. Another term responsible for the Z1 minus Z2 having negative real part. And they survive in the limit separately.
Okay, thank you.
Any other questions? So I have a question. So you mentioned that if there is no mixing, you can recover deformation quantization algebra from this BOA from 4D.
Yes, that's all what we believe. Yes.
Okay. So the Higgs branch is of 4D and 3D the same because there is no quantum correction.
Yes.
And from BOA, if you take associated variety, you can recover the Higgs branch. Whereas I mean, deformation quantization, you just take the whatever H bar or Q equal to 1 limit, you get the just if you take spec or something, you get the Higgs branch. Is there a relation between taking associated variety and just taking classical limit? I mean, do you understand the relation?
It's not fully understood. Okay. So from this little computation in here, certainly taking the 0 mode is responsible for sort of make the bridge between this approach and the Beam-Rastali approach. And it's not fully understood. Okay. There are some relevant discussion also in Delishenko's paper on the similar question.
Okay, I see. So this Delishenko's paper discusses juice algebra, right? juice algebra of the 3n equal to 4, coming from 3n equal to 4.
Right.
How does it related to your story?
So it's that, I would say that, so starting from VOA, you can have two Poisson algebra. You can get the C2 algebra and the Juice algebra.
Yes.
And they are also related by a projection map from, I think, from the Juice algebra to the C2 algebra.
Mm-hmm.
And this, I think this taking the zero mode is sort of a way to land us onto the Juice algebra. But somehow one should also quotient remove all the nilpotent elements or the excessive operators. So that would finally land us onto the Beam-Rosales conjecture, the reduced version of the C2 algebra.
I see.
So, sorry, I should maybe this. I think this procedure, do this in one go. That should be the correct way of saying that.
Oh, I see.
With how to disentangle what's happening in between, how to go from one to the other.
Mm-hmm.
But
Okay.
it should be able to study clearly.
Okay. Any other questions? Okay, then let's thank the speaker by whatever method.
Thank you everyone for your attention.
Questions? Yeah, question. Do you have question?
I don't think so. There's
Oh,
no
okay,
hand.
okay. So this seminar series will take place Wednesday this time, and if, I think in the audience, next speaker is June Nam-Gung. He's going to talk about the 60 Cauchy formula, and then after the Futoshi Yagi will tell us about the 5D complete prepotential and so on. So if you have a suggestion and so on, please let me know. And please inform this seminar series to relevant people. Yeah. So yeah, thank you very much.
Thank you.
If you have, so let me open this, close the recording, and then, and if you have further informal discussion, you can just, I think he's happy to discuss. So yeah, maybe if you have some,
Yes.
want to do the informal discussion, please, yeah, remain here and ask him.